So welcome students, welcome to NEET Rapid Revision Series NEET. Today's one shot number 5. So hope all of you are doing very good practice, very well practice. Hope all of you are well. We are back with this. Today's chapter is that we are going to devise, that is the gravitation. Okay. So if I talk about this particular chapter, so this chapter is little bit easy chapter, but this chapter is scoring chapter as well as more number of question has been asked. Like on everywhere we are expecting 2 questions minimum from this chapter. So we can see that starting from 2014 to 2024, 2 questions are minimum they are asking from this, and only in this 2019 and 2020 we are expecting 1 question. So this year also minimum 1 question they will definitely ask. And what are the different topics, some major topics that we are going to cover. And yes, so let's start our journey for today. So what is our goal today? So Newton's law of gravitation, we already know from class 9th, we are discussing what Newton's law of gravitation and gravitational field for different point masses that we are going to discuss today. Then acceleration due to gravity, the maximum questions has been asked from this. What is acceleration due to gravity and its variation over different depth, height and different points they are asking from the acceleration due to gravity. The different questions they are asking from this. Next is gravitational potential energy and escape velocity questions. Basically, if they are asking some little bit tricky question from this chapter, they will be asking from conservation of energy. That is some of the potential energy and kinetic energy, like that they will be asking. And some question has been also asked from the escape velocity. Last part, but not the least part, what is that? Orbital velocity and satellite motions. So in this case, we'll be asking what is the time period of the satellite. They'll be asking what is orbital velocity of satellite, what is energy, potential energy, total energy, kinetic energy. And also in this, Kepler's law of planetary motion is also there. So let's begin our journey with this. First one is gravitational force and field. So basically we know that, for example, 2 masses are there, m1 and m2. They are separated by some distance over here, distances r. So both the force of attraction will be there. This m1 will attract this m2 and m2 will attract this m1. So force that will be acting here, that is F12, and this force will be that is acting F1, F21. So this, if write this particular term, will be writing that. So F12, force acting on 1 by 2 is equals to force acting on 2 by 1, and this value is given by G m1 m2 divided by r square, where m1 and m2 are the masses and r is the distance between those 2 masses. If you talk about the different properties of the force, this force is central force. So what is central force? That is acting between the center to the center to the center of the masses sphere we have. This force is also conservative force. We know that conservative force, that is work done by this force will not depend on part taken. This force follows the inverse square law, always attractive for given condition. What is G here? Gravitational constant 6.61 10 to the power minus 11. M1 M2 are the masses. R is the distance between the 2 masses. So if you talk about the gravitational field, so gravitational field at any point, so gravitational field at any point is defined as whatever the, suppose if you want to find what is gravitational field, put one test mass over here, and what is the gravitational force that is acting on this particular mass divided by mass itself. So this will give gravitational field at that particular point. Yes, of course this is vector quantity, this is also vector quantity. Direction will depend on the direction of the force. So if you talk about this gravitational field, so gravitational field due to first one, point mass. So gravitational field due to point mass, that is given as, so gravitational field due to point mass, if you talk about mass m is there, at this particular point we want to calculate what is gravitational field, distances r. So gravitational field at that particular point is given by E is equals to G m divided by r square. What is r here? R is distance from that particular mass. So this is point mass, gravitational field due to point masses over here. Second, if you talk about the gravitational field due to system of the masses. So how we define the gravitational field due to system of the masses? If you have multiple mass, not single mass over here. So this m1, this m2 and this m3, and at this particular point, so this particular point, if you want to calculate what is gravitational field, so distance you have to calculate with respect to r1, this will be r2 and this will be r3. So gravitational field at point P will be because of this m1, m2 and m3, that we have to superpose in form of the vector sum. So gravitational field will be given by E1, vector E is given by E1 plus E2 plus E3. If you have number of masses like this, so gravitational field will get. Further, if you see the gravitational field due to ring, the gravitational field due to ring. So if we have ring where the mass is distributed over its circumference, and we want to calculate what is gravitational field on its axis, At this particular point, if you want to calculate distance from this particular point from the center is x and radius is r. So this point, gravitational field, if you want to calculate, E is equals to G capital M into distance is x divided by, so G capital M divided by this r is square plus x square to the power 3 by 2. And we also have graph for this. If you see the graph of this, the gravitational field intensity will be, if you go on the both the side, so if you go on the both the side, so this side, so this particular point distance is r by root 2, and this particular point distance is again r by root 2. At r by root 2 on the positive side, r by root 2 on the negative side, the gravitational field value is maximum. So at this particular point, gravitational field is maximum. At this point also, gravitational field value is maximum. So this is gravitational field due to ring. If you have gravitational field due to rod, if you have rod, so rod is the mass in which the mass is distributed over the length. So this is the rod over here. So at this particular point on the axis of the rod, distance from this is r and length of the rod is L. So if you want to calculate what is gravitational field, G M divided by r square, just now we discussed, that is for the point mass, right? So just r square is distance, r square you break into two parts. One r you write for this, that is r, second r you write in terms of the r plus L. So gravitational field due to rod is given by G M divided by r into r plus L. So this is gravitational field due to rod. Second, if we have gravitational field due to sphere. So gravitational field due to sphere. Now a sphere will be two types. First is hollow and second is solid. So for example, let's say if we have hollow sphere. If we have hollow sphere, the gravitational field is given by at this particular point. So gravitational field due to hollow sphere 0.1, 0.2 and 0.3 if you take. Distance always from the center, this will be capital R and this will be small r. So gravitational field at 0.1 will be 0 if it is, gravitational field at 0.1 will be 0 if it is hollow sphere. At 0.2, that is on the surface, this will be Gm divided by r square, where r is the radius. At 0.3, G capital M divided by r square, where r is the small r is the distance from the center of the distance from the center of the spherical shell or hollow sphere. And if they're asking graph for this, on this side if you plot E, on this side if you plot R, initially E is equals to 0, that's r equals to 0 to r equals to capital R, E value will be 0. So from this particular point to this side, it will be 0, and after this it will keep on decreasing like this, that is rectangular hyperbola. So this point that we should keep in mind, inside will be 0. Moving next, that is if we have solid sphere. If we have the solid sphere, what is the gravitational field intensity? So solid sphere again depends on 3 points that we are going to discuss. We are first particular point, that solid sphere masses will be distributed. First particular point, that is any point inside the solid sphere. So at this particular point, if they are asking what is gravitational field intensity, R, this is capital R, second point, and third point, that is again distance is small r. So at point 1, E is equals to G capital M, where M is the total mass, into this distance how much, r divided by r cube. Second, E2 value will be given by this, at this particular gravitational field on the surface is given by G capital M divided by r square. Third particular point, E3 value is given by G capital M divided by small r square. And if you draw the graph for this, here you can see that it is directly proportional. So graph will be looking like this and like this. So this will be E versus small r. So this particular point, that will be r. So this is gravitational field due to solid sphere. So these are the gravitational force and fields. If we talk about the acceleration due to gravity on the surface of the earth or any planet. So suppose if we have any planet like this, if we have, so let's say this is the planet, and we want to calculate on the surface of the planet what is the acceleration due to gravity. So mass of the planet we can take on the surface, this particular point if you want to calculate. So G value is given by, I am writing direct formula over here. G at the surface is G capital M divided by r square, where r is the radius. G at the surface Gm by r square. At any point, suppose you want to calculate this particular point, and this point is at height, how much height? H height from the surface of the earth, and this will be r. So this particular point will depend on two things. First is if H is very smaller than r, then direct formula we have GH is given by G at the surface into 1 minus 2H by r. This particular formula will be using when the height from the surface should be less than 100 km. Then we'll be using this. Second, in the same case, At the same height, for the same height, if they're asking G value, so if G and if H and R are comparable, means we can compare both, means H is little large, H is little large, H is comparable. In that case, we'll be writing this GH is given by G at the surface divided by 1 plus H by R ka whole square. G at the surface divided by 1 plus H by R ka whole square. So this is what we are getting at this height. How it varies with height at the surface, Gm by R square, Gm by R square, where M is the mass. At any point inside, distance from the surface, we can take it as D. So at this particular point inside, if they're asking what is the acceleration due to gravity, so at this particular point, G at depth D is given by Gs into 1 minus D by R. Gs into 1 minus D by R, where D is the depth from the surface we have to go. This depth that is from the surface, and this is acceleration due to gravity on the surface. So this is what we are getting, and we know that our Earth is little bit having less radius of curvature at the poles and more radius of curvature at the equator. So G at the pole is greater than G at the equator. So this thing also you keep in mind. Pole gravitation, gravity at the pole is little bit higher than gravity at the equator because radius of curvature is less here. Okay, so these are the points that we have in acceleration due to gravity and gravitational field. Let's do some of the questions based on this. So question number 1, what question is saying here? Body of mass how much 60 gram experiences a gravitational force of how much 3 Newton when placed at a particular point. The magnitude of the gravitational field intensity at that point is given by, so gravitational force dimension is 3 Newton. They're asking the gravitational field intensity. So what is gravitational field intensity at given point? Force divided by mass, that's it. So what is force? 3 Newton divided by mass. What is mass? 60 gram. 60 into 10 to the power minus 3. So this will be 3 into 10 to the power 3 divided by 60. 3000 by 60 we are getting how much? 50 Newton per kg. That is option B. So at that point the gravitational force divided by mass we are getting that is 50 Newton per kg. Answer is option B. Clear? So let's moving to next question over here. The question is coming from where? Acceleration due to gravity. The mass of the planet is how much? 1/10th of the mass of the earth. So here mass of the planet MP is equals to mass of the earth divided by 10, and its diameter is half of that of the earth. So diameter of the planet is half of the diameter of the earth. So obviously radius of the planet will be half of the radius of the earth, yes or no? The acceleration due to gravity on the planet should be given by, so if you talk about the G is given by G capital M divided by R square. G depends on this, capital J is the gravitational constant, that is the constant. This is the mass, it depends on the mass, it depends on the radius as well. So here I can write that is G on the planet divided by G on the earth is equals to mass on the planet divided by mass on the earth multiply by radius of the planet, sorry this side inversely proportional to radius, so here will be radius of the earth divided by radius of the planet whole square. So solving this, Gp by Ge, that is G at the earth, is given by mass of the planet is how many times? Me by 10. So this ratio will be 1/10 into this radius of the earth by radius of the planet, that will be 2. So radius of the earth by radius of the planet, that will be 2. So this will be 2 ka square we are getting. So we are getting how much? So G at the planet is equals to G at the earth into how much? This is 4/10. So solving this, 4 into G at the earth. What is G at the earth? 9.8 we have to take divided by 10. So 9.8 into 4 divided by 10, answer is 3.92. Answer will be 3.92. Moving some more questions to it, like in terms of the variation with height and variation with depth we have to see. So variation with height we know GH equals to G S into 1 minus 2H by R. Why I am using this particular formula? Because height they mentioned is how much? 1 kilometer is equals to, is same as that depth D below the surface of the earth. So GS into 1 minus D divided by R. So from here we can compare this. This everything will get cancelled. Remaining is how much? 2H is equals to D. So what is H? H is 1 kilometer. So this value, that 2 kilometer depth, distance of 2 kilometer depth, the variation of the G value is same as that of the 1 kilometer height from the surface. Next, if the R is radius of the earth and G is the acceleration due to gravity on the earth's surface, then its mean density of the earth will be given by. So what is G value? Just now we discussed, that is G capital M divided by R square. They're asking in terms of the, they're asking density of the earth. How can you write density of the earth? Mass. What is mass? Density multiplied by volume. So G is given by, that is G divided by R square into mass. What is mass? Density multiplied by volume. So what is volume? 4 by 3 pi r cube. So this R square, this cube will get cancelled. How much we're getting this? We want to write rho. That's it. So this will be 3G divided by 4 pi G rho. Sorry, 4 pi G. 4 pi G R. Okay? 4 pi G R. 3G divided by 4 pi RG. So this will be the correct answer over here. So here only one formula that we are using, G is equal to Gm by R square. Mass we have to convert into density multiplied by volume. Your answer is here only. Clear? Okay, moving next, all of you. So this side, what question is saying? A body weighs how much? 200 Newton on the surface of the earth. On the surface of the earth, so there is one object, and that object is weighing how much? 200 Newton. How much will it weigh halfway down to the center of the earth? So if the same body is taken halfway down to center of the earth, so in that case, how much it will weigh? So what is the weight at this particular point? M into G. Okay. What is the weight at this particular point, all of you? As we are going, digging the earth, we are going inside the earth. How much distance? D. What is this distance? Halfway down. So radius is R. So this will be R by 2. So inside, mass will not change, but what will change? G will change. How much G will change? G into 1 minus D by R. So this particular value is how much dimension? That is 200 Newton. So whatever this value, W is equal to M into G into 1 minus D. What is D value? What is D value? R by 2 2R. So we are getting this W dash is mg by 2. If this one is 200, so this one will be 100 only. Answer is option C. Clear? Like this type of question they are asking. This all are previous year questions which I am solving here. Second is acceleration due to gravity on the planet A is 9 times. Acceleration due to gravity on planet A is how many times? 9 times. Acceleration due to gravity on the planet B. A man jumps to a height of 2 meters. So on this planet, man jumps to height of 2 meters. So HA is 2 meters on the planet A. What they're asking, what is the height jump by the same person on the planet B? So how the height will depend on G? We know that from the kinematics, H is depends on V square by 2G. If the G value is less, then height will be more. If the G value is more, then height will be less. H is inversely proportional to 1 by G. That's it. So here H is inversely proportional to 1 by G. So here we can write that is HB by HA is equals to GA divided by G. So HB by HA, putting the values here, HB by HA. What is HA value? 2 is equals to GA by GB. So G at A, how much we have? 9 GB divided by GB this. This will get cancelled. How much? What is HB value? 2 multiplied by 9. We are getting here 18. So answer is option B, that is 18 meters. Clear? So let's solve this particular question. Action due to gravity. Again, question is coming like a body weighs how much? 72 Newton on the surface of the earth. Again, so here we have earth. On the surface of the earth, what is weight of the body? The weight of the body is M into G, and how much that is? 72 Newton. What is gravitational force on it at height equal to radius of the earth? If we take this particular object to height of how much? Radius of the earth. So this H equals to R. So for height formula we have, what is this particular formula? That is W is equals to M into G dash, G at height H. Now here the height and radius are comparable, so we won't be using that formula. We will be using this particular formula. That two formulas we have for this. First formula, that is GS, G at the height H is given by GS into 1 minus 2H by R, and G at the height H is given by GS divided by 1 plus H by R whole square. This formula will be using when the height and radius are comparable. So obviously, so in this particular question we'll be using the second formula. So what is that? We'll be writing that. So W is equal to M into GH, M into G at the surface divided by 1 plus H by R ka whole square. Putting this value W dash M into G, putting this value H. What is H? At a height equal to half the radius, sorry. At a height equal to half the radius they mentioned. Yes, half the radius they mentioned, not actually radius. So this side 1 plus R by 2r whole square. Putting this value, W dash, what is mg value? Here we have 72 divided by r cancel, 1 plus 1 by 2, 3 by 2, 3 by 2 square, 9 by 4. This will go upside, 72 into 4 by 9, 9 ones are, 9 eights are, how much we got? 32 Newton. Answer is 32 Newton. The same body will weigh at a height equal to half the radius of the earth. How much weight? 32 Newton. And as we are going above, the weight will keep on decreasing because G value is decreasing. Next we have gravitational potential and gravitational potential energy. So what is gravitational potential? So if we have this particular mass m, gravitational potential energy, what is gravitational potential energy? Two masses are there, m1 and m2. Two masses are there, they are separated by some distance r, then gravitational potential energy is given by minus g m1 m2 divided by r. This is the gravitational potential energy for the two masses system. If you have multiple mass system like m1 is there, second is m2 is there, and third is m3 is there. So we have to calculate in this case, we have to make the pairs that m1 m2 we have to make one pair, m1 m3 we have to make one pair, m2 m3 also we have to make one pair. So here u12 minus g m1 m2 divided by r12. So this one is r12, this one is r23, and this one is r13. So what is u13? Minus g m1 m3 divided by r13. And what is potential energy between these two masses? That is u23 minus g m2 m3 divided by r23. So these are the potential energy for different mass system. We will calculating like this. If we have earth and one mass system, it can be satellite or it can be any other object. Distance of that particular object from the surface of the earth is h, and radius of the earth we can write it as r. So this center distance from the mass is small r, and what is small r? R plus small h. What is gravitational potential energy for this earth and this mass system? We will be writing this minus g capital M small m divided by what is distance? R plus h, or u we can write here minus g capital M small m divided by small r, where small r is the r plus h. In some of the cases, if mass is near the surface of the earth, this h value will be negligible. H is very less than r. In that case, we will be writing, in that case, near the surface of the earth, u value is minus g capital M small m divided by r, where capital M is the mass of the planet or the earth, or small m is the mass of the object, right? So this we are getting gravitational potential energy. Okay. So let's see gravitational potential as well. So what is gravitational potential? So gravitational potential at a point is defined as gravitational potential energy divided by mass, u divided by mass. So if you have mass m1, second mass is m2, at this point you want to calculate what is gravitational potential energy. What is gravitational potential? So gravitational potential will be given by gravitational potential energy divided by mass. So V is equals to what is gravitational potential energy? Minus g m1 m2 divided by which mass is kept over here? M2 divided by m2. That's it. If they're asking at point 1, what is gravitational potential? So it will be like again u by m1. Why m1? Because m1 is kept over here. This v1 will be writing this minus g m1 m2 divided by m1. So this m2 m2 get cancelled. This will be minus g m1. This r will also be there. Sorry. Yeah. So this side m1 m2 cancel. So what is u1? Minus g m2 divided by r. And this side minus g m1 divided by r. This will be v2 at this particular point. So due to point mass, if we have gravitational potential due to point mass, again, so this is the mass over here. At this particular point, we want to calculate what is gravitational potential. So Vp is given by minus g m divided by r, where r is the distance of that particular point from the mass. This is due to point mass. Due to system of the masses, again, no need to worry because gravitational potential is a scalar quantity. No need to worry about the direction as well. So this will be due to system of the masses if we have. So if we have multiple system of the masses, what is gravitational potential energy? So mass m1, mass m2, and mass m3. So this particular point, we want to calculate what is gravitational potential. We have to calculate individually for this mass m1, for this mass m2, and for this mass m3. So v1, vp will be given by for this mass. Let's say this one is r1, this will be r2, and this will be r3. So minus g m1 divided by r1. Next, minus g m2 divided by r2. Next, because of this mass, minus g m3 divided by r3. So this is the net gravitational potential at point P because of all three masses place certain distance from this particular point. I hope this is clear. Moving to next part, that is gravitational potential due to ring. So if you have ring like this and they're asking what is gravitational potential at this particular point P. So mass of the ring is m, radius of the ring is r, and this distance is x. So whatever this, so this distance we can calculate. This one is r, this will be x, under root this will be r square plus x square. So this particular point gravitational field is given by minus g capital M divided by this. We have to take this distance, that is under root r square plus x square, under root r square plus x square. Next, if they're asking gravitational potential due to hollow sphere or spherical shell. Gravitational potential due to hollow sphere or spherical shell. So hollow sphere means inside there is no mass. So we'll be taking 3 points, 1 point over here, second point over here, and third point over here. So just now we discussed the gravitational field intensity at different points. We also saw the graph of this. So inside point gravitational field is 0, but not the gravitational potential. On the surface, what is gravitational potential? Gravitational field plus gm divided by r square, that is on the surface. And after this it will keep on decreasing, that is E is inversely proportional to small r. So this is the gravitational field, and here E is directly proportional to r. This side E is inversely proportional to small r. This is gravitational field over the different points, that is inside point as well as outside point on the surface point. Same if we discuss for the gravitational potential. So gravitational potential will be given by, so this particular point 1, distance from this is r, this will be capital R, again this will be small r. So gravitational potential at point 1 minus gm by capital R, it will not be 0, and this value will be constant inside throughout this hollow sphere, that is spherical shell. Second, at point 2, what is gravitational potential? Minus gm by r, again on the surface as well as inside will be constant. So this will be constant on the surface. Third point, that is outside point, the gravitational potential is given by minus gm divided by small r. So this all we have to remember for different points. And if we talk about the graph will be like this. So from this, if we draw on the negative side, we have to draw. So this side, this is v, and this side r we have to draw. So initially it will be like this, up to which when r is equals to capital R and this is r is less than capital R, this side it will keep on increasing like this. As this value is negative, so this particular point minus gm by r, this value is constant over this from r equals to 0 to r equals to capital R, and after that it will, v is inversely proportional to minus 1 by r. Clear? Right. Last part, that is the gravitational potential due to hollow sphere, due to solid sphere. So gravitational potential due to solid sphere, if you see. So if you talk about the solid sphere, again we'll be taking the different points. The first point, that is inside point, distance of that particular point from the center is smaller. Second point on the surface, and third point outside the surface. So if you talk about this, any point inside, it is given by minus gm divided by 2r cube, 3r square minus small r square. Yes, formula is little bigger, but we don't have choice, we have to memorize this. So v1 we can write minus gm divided by 2r cube into 3r square minus small r square. So in this case, r will be less than capital R. And if you talk about the center, exactly the center, what is r value? If I take exactly the center, what is r value? 0. Put r equals to 0 here. So the gravitational potential at the center is given by minus gm divided by 2r cube into 3r square minus 0 square. So we exactly the center, we are getting this minus gm 3gm divided by 2r. Next particular point, if we talk about this gravitational potential at point 2, that is minus gm divided by capital R. It is the same as that of the hollow sphere. Next we have gravitational potential at point 3, that is outside point, that will be minus gm by small r. This will minus gm by small r. And if I ask you what is a graph, the graph will be like this. Initially, that is v versus small r, graph will be like this. Initially it will start from this, then it will go like this. So this point is the inflation point where the graph changes its shape. So from this side to this side it is parabola, and from this side to this side it is hyperbola. So this particular point r is equals to capital R, this is r equals to 0, and this will give us the potential at the center, V at the center. This will give a potential at the surface, and this side greater than, that is distance more than capital R. That's it. So here this is the graph for this. So these are the gravitational potential we have. Gravitational potential. If you talk about the escape velocity, the one simple thing is that what is escape velocity? That minimum velocity that should be provided to any object so that it reaches to infinity from the earth. It should not return back to the earth. That minimum velocity is what you define escape velocity. So this we are getting in from the conservation of energy. If you are getting from the conservation of energy, how much velocity that it should be giving? Should be taking the energy from here, kinetic energy initial plus potential energy initial equals to, at this point, infinity point, potential energy final plus kinetic energy final. So those derivation I'm not doing right now. So I can write here initial plus potential energy equals to final plus, like this. After solving this, what we are getting? The escape velocity formula is given by under root 2gm divided by r. Under root 2gm divided by r if you are throwing from the surface of the earth. And the same time, escape velocity also in terms of this, in terms of the mass, in terms of the mass density. So this, what is mass? Mass we can write in terms of the mass is density multiplied by volume. So 4 by 3 pi r cube. So this 1 r will get cancelled. So this escape velocity from the surface of the planet is given by this 4 pi 8 pi g rho r square by 3. This will be escape velocity from the. In terms of this, if we write v escape velocity in terms of the action due to gravity under root 2gr, and how we are getting this? You put what is g? G is equals to gm by r square. So this side will go, this side gr square equals to g into m. So putting the value of gr square, that is gm equals to gr square, we will getting this under root 2gr. So this one, this one, this one, both will be useful in solving the problems. And on the surface of the earth, the orbital velocity of any satellite is given by under root g capital M divided by r, and escape velocity just now we discussed under root 2gm divided by r. So ratio is given by ratio of this given by root 2 times of 1. Okay. So let's see some of the questions from the gravitational potential as well as escape velocity. So here two bodies of mass m and second body is mass 9m. They are having how much distance? They are having distance r apart. The gravitational potential on the line joining the bodies where the gravitational field equals 0 is given by. So this particular point if you want to calculate. So let's say where the gravitational field is 0, first you calculate that point. We have to calculate that point. So at this point, let's say gravitational field is 0. Distance of this particular point is r1 and distance of the same point from the 9 mass is r2. We have that direct formula, neutral point formula we have. So two masses will be there. Between the two masses where the exact gravitational potential, exact gravitational field is 0, that neutral point formula that we discussed in the classes, what is that? R1 will be given by under root m1 into r divided by root of m1 plus root of m2. So this r1 let's calculate. So this m1 into r, where r is a total distance. So this root of m multiplied by capital R divided by root of m plus root of, how much we got? Second mass is having 9m. So this will be 9m. So this we are getting under root m into r. So this root m plus 3m. So this we are getting r by 4. All of you getting this r by 4. If this one is r by 4, two masses are there, mass m, second mass is 9m. So we got this particular point where the gravitational field is 0. So this will be r by 4. So obviously this will be how much? 3r by 4. If this one is r by 4 means, so that will be 3r by 4. So at this point, if you want to calculate gravitational field, will be because of this mass as well, because of that mass as well. So minus gm divided by r by 4. Because of this, minus g into 9m divided by what is distance of this point from this? That is 3r by 4. So this will go up. So we'll be writing gravitational potential at point P. This is minus 4 gm divided by r. And this side we have minus 9 into 4, 36 by 3. So this 12 gm divided by r. So we are getting this minus 16 gm divided by r. Answer is option B. Answer is option B. Let's again, the question is coming from this escape velocity. So escape velocity of the earth is E, escape velocity for the earth is V. The planet is having 9 times that of the earth and radius is 16 times that of the earth. So what is the escape velocity? Now they're talking in terms of the mass and radius. We have certain formulas. We'll be using the one which is having mass and radius. So V is equals to under root 2 gm divided by r. So V is proportional to root of mass divided by radius, right? So velocity of the planet, escape velocity on the planet by earth is given by root of mass on the mass of the planet by mass of the earth multiplied by inversely proportional to radius. So this will be radius of the earth divided by radius of the planet. So solve this. Vp by V is equals to root of how many times? The planet is having 9 times the mass of the earth. So 9 me divided by me into this side. How much radius? Radius is 16 times that of the earth. So this radius re. So what is radius rp? 16 times of this radius of the earth. That's it. So this will get cancelled. How much you got? 9 by 16. 9 by 16 root 3 by 4 we are getting. So what is Vp? So Vp we are getting 3V by 4. Clear? So answer is option C. 3V by 4. This question, the escape velocity from the earth's surface is V. The escape velocity from the surface of the another planet having radius 4 times that of the earth and same mass density. We won't be using the same formula as this one, under root 2 gm by r in this case, because what is the reason behind? They have given in terms of the mass density. So we have to write in terms of the mass density escape velocity. What is escape velocity in terms of the mass density? Under root 2 g m by r, right, in terms of the mass density. So this will be 2 g divided by r into what is mass? Density multiplied by volume. So volume of the sphere is, all of you know this, 4 by 3 pi r cube. So this, if you solve this, we'll be getting whatever the value we are getting, root of this 4 pi g rho into 2. So this will be 8 pi 0 divided by 3 into r square. So VE is proportional to root of r square. V is proportional to r. So radius is how many times? Everything is constant. Rho is constant, pi is constant, g is constant, 8 is constant, 3 is constant. Radius ka square. So V is proportional to r ka square means V is proportional to r. So radius is how many times? Radius is 4 times. So velocity will also be 4 times. Clear? Velocity will also be 4 times. Next we have, read this question over here. The topic is interstellar speed. What is interstellar speed? Far away from the surface of the earth in infinity, what is the speed of any object? That is we define as interstellar speed. So here the escape velocity of a body on the surface is 11.2 km per second. So we are throwing with how much? 11.2 km per second. That is escape velocity. If the same body is projected upward with a speed of 22.4 km per second instead of 11.2, if you are throwing with this much speed, what will happen? How much distance? Infinite distance, that is somewhere in the space. Whatever the velocity they are asking, upward with this. So let's say if I am throwing with speed v, you can note down interstellar speed is given by under root v square minus v square. And how we are getting this? We are getting from the derivation of the conservation of energy. Right now we are not describing that, so we have to just focus on this. Interstellar speed is given by v. V is with how much we are throwing with, and v is the escape velocity. And what is this v? Velocity interstellar. So this v interstellar at any point on this space, how much speed will be there, that we have to calculate. So what is v? We are throwing with speed v. What is v? V square minus, and what is this? 11.2. I can write here 2 times of v, yes or no? Because this is 22.4 and this one is 2 times of 11.2. So whatever we are throwing with, that is v, is 2 times of this. So I'll be writing, this will be, I can write here 2ve whole square minus v square, that is instantaneous speed is given by root of this 2v square minus v square. So this will be 3v square. So what is v instantaneous speed? That is root 3 times of ve. That's it. We have to multiply by root 3. So just 11.2 multiply by root 3, that is instantaneous speed we are getting. So just multiply with this 11.2. Okay, answer is only given in terms of the root 3. Answer is option D. Okay, answer is option D. So these are the questions that is coming from the escape velocity. Again, two important topics, that is action due to gravity and escape velocity, that is covered so far. Mostly question has been asked from there. Some more questions, let's see, from the gravitational potential and gravitational potential energy. In finite number of the bodies, each of mass 2 kg are situated on the x-axis at distance of 1 meter, 2 meter, 4 meter, 8 meter respectively from the origin. So if you talk about this, different bodies are there. So this is x equals to 0. Next we have x equals to 1 meter. So at 0, this is 1 meter, this side 2 meter, this we have 4 meter, and this will be 8 meter, and so on. Different bodies are situated on that. They're asking what? The resulting gravitational potential due to this system at origin will be given by. So because of this gravitational potential, so because of this mass, how much mass is kg? Everywhere it is kept 2 kg. So this side 2 kg, this one 2 kg, everywhere it is kept 2 kg. So let's say I'm taking this as mass m. So at this point, if I want to calculate, so gravitational potential at point origin will, because of all the masses, that is v1 plus v2 plus how many? Total masses, all the masses. So what is v1? Because of this mass, minus g, I'll be writing in terms of the m, then I'll substitute, minus gm divided by what is distance? 1. Minus g m divided by what is distance? 2. Minus g m divided by what is distance? 4. Like that. Minus gm divided by what is distance? 8. And so on. It will keep on continuing like this. So if I take the common, so gravitational potential at point P is given by minus g m common. This will be 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up to, sorry, 1 by 2 plus 1 by 4. Sorry. This side we are getting 1 by 2 plus 1 by 4. Next is 1 by 8. And like this. So we can check this particular term, that is we have GP, and we know this, solving this particular GP. So this is common ratio is A, and this one is R. So the first term is A and R is 1 by 2. And what is formula for this? A divided by 1 minus R. So this minus G M into A is the first 1 kg, or 1 second is 1 minus R. What is R? 1 by 2. So how much we got? Minus G M divided by 1 minus 1 by 2. So this we are getting 1 minus 1 by 2, we are getting this A by 1 minus R. So this will be 2 times. So mass, putting the mass over here, what answer will be getting? So minus G into mass is 2 into 2. How much we got? Minus 4G. So gravitational potential, the net gravitational potential at that particular point is given by minus 4G summation we are getting from the GP, geometric progression. A particle of mass m is situated at the center of the spherical shell of mass, same mass and radius a. The magnitude of the gravitational potential at a point situated at distance a by 2 from the center will be. So here one particle is there, a particle of mass m is situated at the center of the spherical shell. This spherical shell is also having mass m, and this having radius a, and there is one more mass kept. This particle mass m is situated at the center of the spherical shell of same mass. So this is also a mass m. What they are asking? The magnitude of the gravitational potential at a point situated distance how much? So from this particular point, distance is a by 2. So at this point we want to calculate what is the gravitational potential. So because of this point mass, I can directly write minus g m divided by how much distance? A by 2. But because of this spherical shell, inside what is formula? Minus gm by r, where r is the radius of the spherical shell. So this minus g capital M divided by A. So gravitational potential at point P is given by this minus 2 gm divided by A minus gm divided by A. Answer is minus 3 gm divided by. So this will be, answer will be, if they are asking magnitude, we have to take the positive. So that is 3 gm divided by A, where m is the mass, given mass. So here this particular question is saying that a body of mass m is placed on the earth's surface, which is taken from the earth's surface to height h is equal to 3r, the change in gravitational potential energy. So suppose if this particular point mass is there, mass m is taken to little height h, from the work energy power we know what is difference in potential energy, delta U. What is delta U? mgh, right? If it is taken small height h from the surface of the earth, the change in potential energy mgh. But suppose if they are asking little bit more distance of the height. So suppose if this is the earth and they are asking little bit more distance, it is traveling some more distance, that is height is more comparable to radius of the earth. In that case, whatever the change in potential energy I'm writing here, you can note down direct formula. What is direct formula? So height is h. So up to this particular formula we will be using in case of work energy power questions if the height is very small. But this particular case we'll be using delta U. What is delta U? mgh divided by 1 plus h by r ka whole square. So note down this particular formula for change in gravitational potential energy when it's taken to some height h. So mgh divided by 1 plus h by r ka whole square. That's it. So this will be writing, put the values, and what is h value here? Height equals to 3r. Putting this, so this mgh divided by 1 plus h by r. Now whole square will not be there. So this just 1 plus h by r. So this will be 1 plus h by r. So this is the height delta U. So putting this value, we are getting here mg into 3r divided by 1 plus 3r by r. So we are getting this. What is delta U? So solve this. 3mg divided by 1 plus 3, that is 4. We are getting this 3mg r divided by 4. R, this is the formula that we have to use over here. Up to here you already know. You can note down this. That is mgh divided by 1 plus h by r ka 1 plus h by r. That's it. When it's taken to some height h, 1 plus h by r. So answer will be here 3 by 4 mgr. I hope this is clear to everyone. Moving next particular questions. Again, similar question is there based on this. What they're asking here? Work done to raise the mass. From the previous question, they're asking, previous NEET question they asked. In that case, what they're asking? Change in potential energy they're asking here. Now what they're asking? The work done to raise the mass from the surface of the earth to height h, which is equal to radius of the earth. So if we talk about this, if we work done to raise the mass, whatever the work we are doing, if you are doing the work done slowly, we can write here work done equals to delta U. So this particular point is taken to some height h. How much work we have done? H equals to r. So in this case we can write work done equals to delta U. And what is delta U? We know that work done is equal to delta U, that is mgh divided by 1 plus h by r. Put the values, that's it. So mg into h. What is h? H is the r, where r is the radius of the earth. 1 plus r by r. So what we got? That is mgr divided by 2. Answer is option C. Answer is option C, that is mgr divided by 2. Next, this particular question is coming from this escape velocity. So what is escape velocity? A particle of mass m is projected with a velocity how much? V is equals to kve. V is equals to kve. So here v is equals to kve. Obviously k is less than 1. So v will be less than k into, sorry. So k is less than 1, where v is the escape velocity. So kve will be less than ve. So particle is not going to, the particle is not going to maximum distance over here. The particle is not going to infinite over here. Particle is going to some maximum distance and coming back. So that's why they're asking what is maximum height above the surface of the earth. So if we are throwing with certain speed v, it will go to some height h, and note down the direct formula again, h max. So what is h max for this? How can we calculate h max? So at this point it is having kinetic energy. At this point it is having kinetic energy will be 0 because highest point it has to come back. So at this particular point kinetic energy will be 0. Whatever the change in kinetic energy, that is also equals to change in potential energy. So delta k should be equals to delta U. And what is delta k? Half m v square. Finally 0 is equals to what is delta U? Change in potential energy. Just now we discussed that. From this point to this point, how much change potential energy? Mgh divided by 1 plus h by r. Mgh divided by 1 plus h by r. So solving this question over here, so we are getting half m v square. What is v? Escape velocity into k times. So this will be k v e whole square equals to mgh divided by 1 plus h by r. So just a second. So we are getting this half m k square into v square equals to mgh divided by 1 plus h by r. 1 plus h by r. So just put the values. So here we can calculate this m or m cancel. So here we can write k square, and what is v? 2gr. root square divided by 2 is equal to this side. We are getting this g into h divided by 1 plus h by r. 1 plus h by r. So this particular term, if we do this square, so this 2 or 2 will get cancelled. So this will be g r k. This side g r k square is equal to g into h divided by 1 plus h by r. So this g and g getting cancelled. So this will go this side. We are getting this r k square into 1 plus h by r is equal to h. So this r k square plus k square h is equal to this side r k square plus k square h is equal to h. So here we can write here r k square is equal to h into 1 minus k square. What we are getting here? H value there we are getting here, that is r k square divided by 1 minus k square. So this is the final answer that we are getting from the maximum height. Only simple formula that we are using here, delta k to delta u, that is half mv square equals to mgh divided by 1 plus h by r. Answer is option A, r k square divided by 1 minus k square. So these are the topics that we have for this escape velocity. And the next we have satellite motion and orbital velocity. So if object is moving in a circle around if the object is rotating or revolving around the earth. So let's say we have the radius of the earth is m, radius of the earth is r, the mass of the earth is m. So this particular point, let's say the earth is this particular point, the satellite is revolving. So due to the force of gravitation, the satellite is revolving in a circle. The gravitational force is providing the necessary centripetal force, and from that we are calculating the what is orbital velocity we are getting. So again, I am not gonna for a derivation part, but just I am telling the gravitational force is equal to centripetal force. From that we are getting the orbital velocity. So what is orbital velocity from here? This height is h. This height is h. So orbital velocity for this particular point will be writing under root g m divided by r plus h. The things to keep in mind is that orbital velocity does not depend on mass of the satellite, whether it is 1 kg, 2 kg, 3 kg, 1000 kg. It will not depend on mass of the satellite. It will depend on mass of the planet and radius of the planet and height of the satellite. So this we can also write in terms of the r. So what is r? R is given by capital R plus h. And what is r? Radius of the orbit. So don't get confused. So this will be radius of the orbit. This will be height of the satellite. Okay, so this will be height of the satellite that we have, and obviously this will be radius of the earth, r plus h. This will be height of the satellite. So this is the orbital velocity. And if satellite revolving near the earth, so this h value is less. H value is less than very r. So here we write v naught, and what is v naught? Under root gm divided by r. In terms of the g, it will be g into r, or in terms of this v naught value will be under root g into r. So this is for the satellite which is rolling near the surface of the earth. Next we define time period. So what is time period? 2 pi r divided by v naught. Time taken to complete one circle. So 2 pi r in this r will be radius of the satellite, radius of the orbit of the satellite divided by v naught. 2 pi r divided by v naught. So time period is 2 pi r. This will be r plus h divided by v naught. For this satellite which is revolving near the surface of the earth, that we can note down this 2 pi under root r by g for the satellite near the surface of the earth. Near the surface of the earth. So this value near the surface of the earth, and this time period is given as approximately for this is 84.6 minutes. So by the time we are having this session, one satellite is already revolving around the surface of the earth by one revolution. This is time period. Further, I can ask question from the energy of the satellite. So what is energy? The potential energy. What is potential energy we have? This is the mass of the earth. Radius is r. This particular point m. Distance is small r. So here we define total energy. What is total energy? Minus g capital M. Here we define potential energy. What is potential energy? Minus g capital M small m divided by small r. What is total energy? Half of this. That is potential energy divided by 2. Minus g capital M small m divided by 2r. What is kinetic energy? The kinetic energy will be given by g capital M small m divided by 2r. So here with that we have relation. here as well, that is total energy is equals to potential energy divided by 2 is equals to minus of kinetic energy. Remember this. Whenever the satellite is changing its orbit from one orbit to other orbit, we have to apply the change in total energy, right? So let's see some of the questions from the satellite as well. So here we have, the question is saying that the radii of circular orbits of two satellites A and B of Earth are 4r and r respectively. If the speed of the satellite A is 3v, then the speed of the satellite B will be how much? So two satellites we have, radii they have mentioned. So V is given by under root gm divided by small r, right? So radii of the circular orbits of two satellites A and B of the Earth are 4r and r respectively. So V is inversely proportional to root of r. So here we can write V2 by V1 is equal to under root R1 by R2, or V1 by V2 under root R1 by R2. So what is the answer here? So this will be getting A and B of the Earth are 4r and r respectively. If the speed of satellite A is 3v, then speed of satellite B will be given by. So this side VB by VA is equal to root of RA by RB. So solving this, VB by VA is equal to RA. What is RA? Satellite A is having 4r and this one is having r. So this, if we solve this, so what is VB value? VB value will be getting from here, that is 2 times of VA. Okay, 2 times of VA, answer will be 6. Second is this one, two satellites of Earth S1 and S2 are moving in the same orbit. The mass of the S1 is 4 times the mass of the S2. The mass of the S1 is 4 times the mass of the S2. Which of the, so they are given the mass and they are asking whether the mass will determine the different points or not here. So option A, what they are saying, the potential energy of the Earth and satellite in the two cases are equal. Earth and satellite, they are asking the potential energy. So what is potential energy? Just now we discussed. The potential energy depends on minus G capital M small m divided by R. So this is the potential energy. It depends on the mass of the satellite as well as mass of the planet as well. So mass is different. We won't say that this will be correct answer over here. Next, S1 and S2 are the moving with the same speed. Yes, let's check this one. So what is orbital velocity? Under root G capital M divided by R. And what is M here? Mass of the planet or mass of the Earth. So here there is no function of small m, that is mass of the satellite. So this one is correct because M is same, R is same. Yes or no? R moving in the same orbit. Same orbit means R same. R will be same. S1 and S2 different masses but same orbit, R will be same. M mass of the planet. Okay, so this one is correct. Let's check this one. The kinetic energy of the two satellites are equal. So kinetic energy of two satellites, what is kinetic energy? Again, the kinetic energy of the satellite depends on, this will be plus G capital M small m divided by 2r, where r will be radius of the orbit. Again, this depends on the mass. This will not be. Last one, the time period of satellite is 4 times that of the S2. Time period should be same. Time period should be same. Why? Because 2 pi r divided by v naught. They are having same radius. They are having same velocity. So this answer is option wrong. Answer is option B. The additional kinetic energy to be provided to a satellite of mass m revolving around the planet of mass m to transfer it from circular orbit of radius r1 to another radius r2. So here we have mass. This mass is m. Radius is how much? This radius is, just a second. So additional kinetic energy of mass revolving around a planet. Let's say here we have a planet and here we have one satellite. The satellite is rolling in this particular orbit. Radius of the orbit is r1. This has to be sent to R2. So this is one orbit and this is another orbit. This radius is R2. So what is the additional kinetic energy that we can provide? So to stay in this orbit, it has certain total energy. To go in this orbit has certain total energy. We have to find that delta of the energy. Then only it can sustain there over here. So here, let's say, so this particular point, what we have to do? The total change in energy, that additional kinetic energy that we have to provide. We can provide only kinetic energy, we can't provide the potential energy. So here we will be writing this delta K. Delta K is total energy final minus total energy initial. Final minus initial. So what is final? So minus G capital M small m divided by, what is final? This will be 2R2 minus minus G capital M small m divided by what is initial 2R1. So this we are getting, solve this particular question over here. So this delta K will be given this G capital M small m divided by 2R1, this minus G capital M small m divided by 2R2. So this side G capital M small m divided by 2, 1 by R1 minus 1 by R2. Clear? 1 by R1 minus 1 by R2. Answer is option D. This is the extra energy that we have to provide. Final total energy, final minus initial. We have to send it from R1 to R2. Next we have, that is Kepler's law of planetary motion. If we talk about the Kepler's law of planetary motion, that we have three different laws. The law of orbits, that planets revolve around the sun. In which orbit? Elliptical orbit, not the circular orbit. So this is law of the orbits. The planet revolves around the sun. So this planets revolve around the sun. So this particular point we call it aphelion, that is distance away from the sun, and this is perihelion, that is nearest distance to the sun. So in this case, the planets are revolving in this particular orbit, and where the sun will be kept at one of the foci of the ellipse. This is law of the orbit. Second is law of areas. And what is areas talk about? Equal areas will travel in equal interval of time. So planet will travel equal area in equal interval of time with respect to sun. So this, if the time interval is equal, so this, if the time interval is equal, so this delta t here also and delta t here also. So here it will be a1 and here it is a2. Then here we define aerial velocity. Aerial velocity, what is aerial velocity? The aerial velocity is given by this a1 by delta t is equals to a2 by delta t. That value will be constant. a2 by delta t, this will be constant. So a1 by delta t is equals to a2 by delta t, and this aerial velocity, that is L by 2m. So this value will be constant, provided that L is the angular momentum, m is the mass over here. L is the angular momentum, m will be mass. So this aerial velocity will be constant. And from this part we are also getting, that is r1 v1 equals to r2 v2. This particular expression says that if the planet is near the sun, it will be travel faster. If the planet is away from the sun, it will travel slower. So this point slow velocity and this point high velocity. So let's solve this particular question over here. At point, different points are there. This point is nearest point and this point is farthest point. So here the velocity will be minimum and here the velocity will be maximum, because this point is nearest point. So nearest point velocity will be maximum. If the velocity is maximum, nearest point means kinetic energy will be maximum. So maximum kinetic energy at A. Next, this is the velocity at which, this is the point at which the distance from the sun is very large. Velocity will be minimum. So here minimum kinetic energy at C. Remaining, that is between. So this will be Ka, then Kb, then Kc. Clear? So this will be Ka, then Kb, then Kc. Option B. Ka, then Kb, then Kc. So this is the last question of this session over here. That is the Kepler's third law of motion. This is the Kepler's second law again. So here we have, what they are asking? The figure shows the elliptical orbit of planet M about the sun. The shaded area as CD. This area of this is how many times? Area of this SCD is how many times? How many times? Is twice the area of this. Area of this. This area, that is this area is double of this. Twice the area of SAB. So in this case, what we have to write? If T1 is the time for the planet to move from C to D and T2 is time to planet from A to B, then what we have to write? So this we can write here. We know that A1 by T1 is equals to A2 by T2. Putting these values over here, directly we can write. So this A1 by T1 equals to A2 by T2. So what is area? SCD by T1 is equals to this side, area of SAB, 2 times of area of SCD, yes or no? Because this is area of SCD is twice. This will be twice, 2 times of area of SCD. So this I will be writing, just a second. So area of SCD, that is 2 times of area of SAB divided by time. How much time is taking from this SAB for time? T1 is time for planet to move from C to D. from C to D, this T1, and T2 is time to move from A to B. So this will here time will be T2. This side area of this area is SAB only, and how much time is taking from this? For this, how much time? T2. So this will be writing this, and T2 is a time from to move from A to B. Sorry, this will be T1. Okay, and this will be T2. So we are getting this. What we are getting from here? T1 is equals to twice of T2. Simple thing is that here area is double, so time here will be double. So this T1 equals to twice of T2. So that's it for today. We cover some of the topics, important topics like action due to gravity. We discuss gravitational field potential. We also discuss gravitational potential energy. We will discuss the escape velocity concept. So keep your preparation as far, solve as much as PRQs as you can. And tomorrow we'll come up with this, that is chapter thermodynamics. And yes, it is very important chapters, because in chemistry also we have, as well as in physics also we have some of the chapters. Some of the topics that we are going to discuss tomorrow, that is first law of thermodynamics, important topics in thermodynamics. Second is different types of process. Different types of process we have. So different types of process means adiabatic process, isochoric process, isothermal process, and isochoric process we have. Last one is cyclic process that we are going to discuss tomorrow. So till then, you prepare well, solve all the formula, solve all the questions, revise the formula, and prepare your best. Thank you.